Thanks for joining us today. I'm John Amond. I'm Professor of Chemistry Emeritus at Montana State University. Part one of this series was about color and how color is what's left over when something is taken out of a continuous white spectrum. Part two, today, we'll use this selective absorption of light to measure the concentration of colored solutions. It's called spectrophotometry and is the most used analytical technique in medicine and chemistry. Here's a slide showing the absorption spectrum of a blue food color, the sample we'll be using today. And if you notice, here's the continuous spectrum and here is the blue spectrum above it, taken with a visual spectrometer. And there's a chunk missing right here in the red. The next slide shows a series of these blue samples, and these will be from the lowest here, which is 20% of the standard concentration, 40%, 60%, and 80%. Let's take a look at these samples sitting on top of the microLAB. We have these solutions sitting on top of the microLAB FS528. On the right are 4 solutions, and on the left is a blank, a distilled water sample. And I have here a graphic showing what is going on down inside of the spectrophotometer. Let's look first at the setup inside the spectrophotometer. We have the LEDs shooting across this sample container. This is a source, this is a sensor. There's a little stir bar down here if you want to stir the solution during the measurement. Let's go back now to what's going on down in there. There are 16 of these narrowband light emitting diodes shooting across the solution. Each one has a sensor across from it, and a sensor at 90 degrees and a sensor at about 135 degrees. Okay, we're going to call up the spectrophotometer Beer's Law program, and the first thing it will ask us to do is to run a blank, and I'm going to set a blank in the sample and in the sample container, and we'll run that, and this should arbitrarily be set into 100% for each wavelength. Okay, there they are, 16 bars showing wavelengths from 360 to 890 in this instrument, and all setting at 100%. Now I'm going to add a sample. This is a blue sample, and I'll just put blue here. And the first sample I'm going to put in has a concentration of 20%. So I'll take the blank out, put the 20% sample in, and let's see what it does. Reads relatively rapidly. You can see this sample absorbed a little bit out here, but quite a bit here in the red orange region. This is a transmission measurement. If I switch to absorbance, which is the reciprocal of that and the log as well, you can see the absorption is greatest right here. If you look at this spectrum right above here, you can see absorption taking place here. Kind of watch that, it's going to get greater as we increase the concentration. I'll add a sample, and this we'll call 40%, and run it. Watch as it takes off here, watch the absorbance measurement. See, it went up here, but this became greater, but it auto-scaled to use space on the graph. Notice this absorption here is greater. Let's try 60%. Okay, the absorption went up, same shape of the graph. 80%. Notice it says here we're using 360 nanometers as the measurement. That's this one. I could put a line on this. I'll go over to curve fit, put a linear line. It's straight, but boy, it's not changing very much at all. On the other hand, it's not absorbing very much. If I click on this one, it'll go up just a little. This will go back down. If I go over to here, see it gets steeper and steeper and steeper as the absorption increases. If we're going to measure an unknown, this would be the best place to do it. Chemists prefer to use absorbance than transmission for spectrophotometric measurements. I'd like to show you why that is. Here's a plot of concentration for that blue sample we just analyzed and absorbance, and if you notice, concentration and absorbance are linearly related. I've set this up with a quadratic plot, which is straight in this case, but if I convert to transmission, it'll give me the curve. And you see here's at very low concentrations, 100% transmission. At very high concentration, it's down to about 5%. and it's a curve, and it's difficult to work with mathematically. If I use absorbance, which is the log of 1 over the transmission, straightens out a very useful relationship. I'd like to show you another display mode. It's called a line graph. If I click this, the absorbance plot changes from a histogram to a line graph. And notice that the color of the graph line is keyed to the color of the spectrum as it goes across. I can make the line wider. I can save the line values if I want to do that. And I can move from one point to another in the spectrum by clicking on the line. And if you notice, the lower graph changes its slope as I move down. So we have two display modes, and you can decide which you like the best. Both of them feed the same concentration graph. Let's take a look at this equation. The y variable, absorbance, is equal to A times B times C in Beer's law. A is what's called the molar absorptivity constant, B is the path length, and C is the concentration. In the equation we looked at just a moment ago, the A and B are combined. But B is a constant because the path length is not changing. If you rearrange this algebraically, concentration is going to be absorbance divided by A times B. The point of this is that absorbance is directly proportional to concentration. You can determine the concentration of almost any colored solution with this technique. Because it's accurate and fast, it's the favored tool for medical and environmental analysis. Thanks for spending time with us today. The next video will show you how fast spec can measure fluorescence and turbidity.